Okay, so hello everyone. So welcome to our this week Progress in Efficient AI seminar talk. And today we're very glad to have Professor Beidi Chen to give us this talk about the efficient LLM. And Professor Chen is he's an assistant professor in the EC department of CMU, and I think you will join the CMU this fall.
This fall. Yes.
This fall, yeah. And she's currently a research scientist at FAR Meta. And before that, she was a postdoc scholar at Stanford, and she received her PhD from the Rice University and a bachelor degree from the UC Berkeley. Her research focuses on efficient deep learning, and specifically, she designs and optimizes randomized algorithms on current hardware to accelerate large machine learning systems. And her work has won a Best Paper runner-up at ICML, a Best Paper Award at IISA, and the Best Paper Award at the USENIX LISA. And she was selected as Rising Star in ECS by MIT and UIUC. So now let's welcome Professor Chen to give us this talk.
Thanks for inviting me. So today I will be excited to talk about this new work on how to use contextual sparsity to perform accurate and low latency generative inference of large language models. Specifically, how we understand this kind of different fundamental computational and memory bottlenecks of inference and design algorithms adapting to the modern hardware and finally improve their efficiency. So this is a joint work with my wonderful collaborators. Right. So over the past few years, this large language models, this wave, has demonstrated impressive performance on various different natural language processing tasks. It powers chatbots, virtual assistants, and maybe customer support system that you heard of, and you can extract and summarize the key information from news articles, research papers, or even legal documents, making it easier for us to just basically understand and access all this relevant information that we don't need to read all of them. And very importantly, we can also use them to generate code or even human-like tasks like marketing, social media blogs, or even creative writing. Yes, the above is generated by ChatGPT. So just kidding. So we have seen all this like new wave of exciting applications because of, we call it, emerging abilities of those large models, such as zero-shot or in-context learning. So they can basically perform a task by conditioning on input and output examples without even updating the parameters. So it's not the same error as like the usual fine-tuning as we've seen before. At least from the current state that we can see all these plots from either GPT-3 paper, OPT, from GPT-3 equivalent from Meta, and Palm from Google, that basically sends out the one key message: scaling is the key that unleashes all these great properties and performance of language model. So for now, the training of large language models, of course, rely on the use of extremely large-scale data, large transformer architectures, and faster computing resources. And we're seeing all these recent large model computations going on across institutes. But the scaling of the model size just means that it will also be very expensive to deploy. Here's an example of OPT 175 billion, which is GPT-3 equivalent. Yes, this example is a little bit out of date. And also curious to know what is the size of ChatGPT or GPT-4. So a simple calculation here shows that 175 billion parameters of FP16 means that at least we need 350 gigabytes memory just to hold the model. So which means that if you have the luxury to have 800 80 gigabytes. You need at least 5 of them just to load the model. And not to mention how much other resources we need to consume and how much carbon footprint you will produce. So except for the model size, which is basically a byproduct of this robust optimization of our parameterized training, is there anything special about the generative inference of large language models? So let's first recall what is good about transformer architectures, especially during the training. So compared to these RNNs or LSTM, one key contributor to scaling or transformer scaling is massive parallelization across sequence lengths. So like what I'm showing here as an example in this diagram, that all this next token generation of ILOF randomized algorithms can always be performed at the same time. However, this is not the case during the inference. So compared to the training, it has very low parallelizability and requires a lot of GPU memory, except for or besides the weights. So let's still look at the same example. Say during the inference, my input is I, and conditional I will generate love, and safe is KV cache because we don't want to recompute it. Then you will generate randomized, and safe is KV as well, so on and so forth. So basically, this generation is like one by one, causing the parallelization problems of original like input sequence. You can parallelize them, but now you can't parallelize them in that degree. And we also need to save the KV cache, which keep increasing the memory allocation. Well, in general, we just can't borrow techniques directly from training or other models like vision transformers because they don't suffer from the same problems. So there's an urgent need to design more efficient algorithms just for the language model inference. Well, to better motivate you to continue listening to this long talk, here is a sneak peek where I could lead you to today. The top table or the headline kind of says that at its best case, which is batch size 1 and low latency, which is like latency sensitive applications, and OPT 175 billion parameter model, Deja Vu can produce the inference, reduce the inference latency by 2.5x compared to our state-of-the-art implementation from NVIDIA called faster transformer, and 6.8 times compared to the widely used Hugging Face implementation, which is very convenient without compromising the model quality. So a small note here is like to get the extreme efficiency and get rid of any overhead, this faster transformer was implementing C++ and CUDA, but our Deja Vu is fully in PyTorch. So to get a better sense on how much speed up this like 16 millisecond means or this 2.5x means, I'll show in the bottom of the table that the generation latency, which is 40 milliseconds in total, the breakdown of this like latency breakdown of batch size 1, prompt length 128, and generation length 128 setting. So you can see that the MLP blocks will basically take around 90 milliseconds, and the attention blocks will take 13 milliseconds. And this communication is basically all-induced across, I assume we're using tensor parallelism across NVLink, then it's around 6 milliseconds. And the other ones like embeddings or layer norm and etc. will cause like 2 milliseconds in total.
对，他做的是把大计量规律 model
Yeah, so I'll continue. So although like this 2.5x seems like we're not hitting the limits, but if you look at the sum of this communication and others, which is 8 milliseconds, it is saying that even we skip all the transformer blocks, we can in maximum get 5x reduction in the latency in maximum. So 2.5 is very exciting. So before we go into the details of today's talk, here's the outline. I first introduce some background knowledge and related work on the approximation algorithm or optimization of language model inference, and then present our main hypothesis, contextual sparsity hypothesis. So which you might not, you have been like curious about and never heard of, but I will explain that in a minute. And then after that, we'll enter the main section of Deja vu, which would contain 3 stages, basically, existence, prediction, and efficiency. So it means that we're going to prove the existence of contextual sparsity, present algorithms to predict it, and finally achieve the efficiency we just saw. And in the end, we're going to show a holistic evaluation of deja vu, including extensive downstream tasks, different model families or model architectures, and its combination with quantization or batch size and more. Okay, let's get started. So there are basically 3 main directions of existing literature of making large language model efficient. The first main category is quantization. So like the ones that you probably heard of, like integer A, smooth quant, zero quant, GPTQ, and so on. So give you a sense of what they're actually doing. So integer 8 is kind of like detecting outliers in the activation and then perform the majority of the computation in integer 8 and only like around 1% of it in FP16. So they separate the ones that you can quantize more and the ones that you can't. For example, GPTQ is basically compressed to like 4 or even 3 by performing like pre-processing of the weights. And then the second big category is the system level optimization, meaning they use like system techniques like offloading, splitting layers to create 4 more layers of parallelization, or schedule the computation of different inputs or layers, like what's the optimal way of loading different layers or inputs. They generally aim for very different settings, like high performance hardware or commodity ones. And this like faster transformer is, we just saw that comparison with Deja vu. So which is the state of art, super optimized implementation from NVIDIA for the latency setting of 800 with NVLink. And the last category is sparsification or pruning, which we've seen this work called sparse GPT. So these are all orthogonal areas and usually excel in different settings. And recently, there's also an active line of research on attempting to apply one or more or a combination of different ones. You probably already noticed that the sparsification section is a little bit blank. So it doesn't have too many methods. So deja vu, what we're going to see later, belongs to this category. And you will see in a second that there's a reason why behind why this is a kind of like more blanked and underexplored area in large language model inference. Oh, comes to my favorite slides. So the idea of sparsity is not new. It has a very long history in machine learning and has driven fundamental progress in statistics, neuroscience, and signal processing. However, it's very challenging to get walk clock time latency reduction from sparsification, while we can still maintain the emergent abilities or impressive performance of those large language models. So this is such an important application and problem. And let's take a look together to see why is it so hard to do sparse inference on GPUs and what are the challenges they all share. First, it is kind of feasible to retrain or iterative proof models at the scale of hundreds of billions of parameters. So the methods like what we have heard for like a decade, like iterative pruning or lottery ticket hypothesis, that those are usually be applied for like smaller scale of the model. So training even one large language model is a headache. So you don't want to retrain or like iterative retraining just to get potentially a better model, right? And second is challenging also to find the sparsity that can preserve those performance or the immersion ability in context learning ability of large language models. So many work has also shown the effectiveness of like task dependent pruning, but maintaining different models for each task conflicts with the task independence goal of those foundation model or large language models. And last, most existing methods, for example, the sparse GPT will adopt unstructured sparsity or maximum utilize the 2-4 sparsity from NVIDIA GPU, which might be efficient in theory or have improvement in theory, but do not take into account of the efficiency of the inference hardware, such as like 800 is high performance hardware or even TPU, which is just optimized for dense computation. So this is an example of the memory access. So the point is like this GPU or TPU, this block device, the access of this red spot is the same access of this blue 4x4 locations. So even with like 99% of the random sparsity, we're likely to access the full matrix because of this. For example, the recent development in zero-shot pruning, like sparse GPT will find 60% of the unstructured sparsity, and they don't have an implementation on which leads to the workload speed up. So what would be an ideal ones for the inference? First, it should not require model retraining, better not updating the model at all. Second is like it should maintain the quality and in-context learning abilities of those models. And the last is you should lead to the actual latency reduction, which is our goal in workload time on modern hardware or best available hardware. So to achieve such demanding requirements, we need to go beyond static sparsity in previous work, which is structured or unstructured wave pruning. Instead, we envision this contextual sparsity, which in the definition is a small input-dependent set of attention heads or MLP parameters that lead to almost the same output as the full model for an input. So inspired by these connections between large language models, inference, and hidden Markov models, or the classic Vatavi algorithm, we hypothesize that even for pre-trained, densely pre-trained language models, contextual sparsity just exists given any input. So this hypothesis, if true, would enable us to cut off specific attention heads or MLP parameters. Those are very structured sparsity on the fly for inference, and without even modifying or retraining or touching the pre-trained model. Okay, so enough for this kind of background introduction and the definition of the hypothesis. We're heading to our main section on the 3-stage towards deja vu. Existence, prediction, and efficiency. So first, it's not trivial to verify if such contextual sparsity even exists. And naive verification is probably a combinatorial problem and very expensive. And the second is like the prediction. So even it exists, it's also hard to predict for a given input in advance. And the last one is like the efficiency. So even you can predict it beforehand, it might be difficult to achieve this end-to-end speed up. So let's take the OPT 175 billion as an example. So the latency of one MLP block is only 0.2 milliseconds on an 8 by 880 gigabits machine. So without a very fast prediction and optimized implementation, the overhead can easily increase the latency rather than reduce it. So first, let's see how do we empirically prove that such ideal sparsity actually exists. So we verify this by a very simple method inspired from just the general pruning community. We just first take one forward pass of the input data sets, anyone, and only keep the top K activations of both MLP and attention has, and see how sparse we can go for those blocks. And the results shows that large language models actually have up to 80% of this contextual sparsity for a given input. So note here that by contextual, it means like for each given input sentence, it will be different ones. So it's data dependent. And the last point is like this contextual sparsity also has much better efficiency accuracy trade-offs we see on this plot, which is up to 7x compared to the non-contextual sparsity or static sparsity. So let me first explain those terms, and then we can take a deeper look at the plot. So the static is very intuitive. It's just like totally fixed, like any other pruning method, just standard pruning. So it's invariant to any inputs or any context. And then non-contextual just means that it's context, is not context dependent, but it's depending on the input token. So each vocabulary or token will have a kind of unique combination of sparsity. And the last is like a contextual, just means we've already seen that for is input dependent, and especially is at each layer. So it's based on the activation from previous layer. You can determine the sparsity for the next layer. So we first plot the average sparsity we impose on these MLP layers. So let's take a deeper look here. We can zero up to 99 at some point, but average like 98-ish activations for a given input token without accuracy drop. So for MLP, it's kind of intuitive that we can find this contextual sparsity because their activation functions are usually ReLU or GALU, and they tend to, they don't like, they filter out the low activations anyway. And a similar observation were made in Lee et al. And but just more extreme. And before looking at it, I was also surprised that we have only around like 1 to 5% of the parameters actually useful for each input. And it's just going more extreme when your model size increases. However, it is also surprising that we can find the contextual sparsity in attention. So finding contextual sparsity in attention is not the same as head pruning. So we cross-check that different examples will have different contextual sparsity, which means that for each of the sentence or like token interactions, not all the heads have informative content, and you don't need to activate all of them to maintain the same accuracy. So although there's like 80% of the parameters were not included in the past for a given example, they might be able to use by other examples or other inputs. So we we try to explain or understand why this happens. So we hypothesize that the attention head is also performing mean shift clustering. So different heads basically learn different projection space to perform clustering. And here we visualize one example or the attention scores of 3 different heads like 42, 43, and 44 for example sentence. So you can see that this like heat map, the darker color means that it has like a larger attention score, higher token interaction. So head 42, even for any like the same token, pairwise token, head 42 and 44 will give heavier attention scores on particular one. But this head 43 is more of a uniform. So which means that they have like different information. So I won't go into the details of all these understandings or observations, but the key takeaway from just the previous several slides is first, contextual sparsity exists. And second, we should be able to design similarity-based sparsity prediction. Okay, so this leads to our next stage on since this exists, how do we predict it in advance? So here is on the left is a simple diagram of transformer models like attention 1, MLP 1, and attention 2, and so on. So let's zoom in one feed-forward layer here. So the existence says that we only need to keep the top K high activations. So which is great news that a lot of computation are wasted, basically like 98 in average is wasted on 175 billion parameter model. But the bad news is that for a given input, you need to do all the computation to know which resulting column are going to give you high activations. So which computation you should actually do, which ones you should not own. In this way, we have no savings. So this reduces the problem on how to predict which columns will produce high activations in a matrix without computing this full matrix or matrix vector multiplication. So next, I will show you how sparse matrix multiplication can be mapped to a near neighbor search problem. And I will introduce a randomized algorithms called locality sensitive hashing, which is the first attempt in designing our prediction. Remember that our core problem is to try to predict which column vector are going to give us high activation without doing the multiplication. Okay, so let's look at this 2-dimensional example. So here's a circle, and this is a query, and here's the a near neighbor, which can be any token that we're looking for, and this is a further away point or irrelevant one. So if we randomly split them with a hyperplane going through their region, what can we observe? So we can observe that it's likely to split the query and further away points, and how much more likely is monotonic to their angle distance to the query. So we can easily extend this intuition, although it's in 2 dimensions and it's also in a circle, that LSH is basically a random space partition algorithm that what we need to remember is it's likely to separate the points that is far away from each other, but unlikely to separate the near ones. And we can compute that probability exactly. So it is commonly used in the application of near neighbor search, which is what we would like to hear. So during the pre-processing phase, the data is usually passed into a set of random neurons. It passes into a set of random hash functions and generate the hash code. And the random hyperplane for splitting the circle we just saw are one kind of those hash functions. And then based on this hash code, these data are assigned to different buckets of the hash tables, and the similar data will be likely to assign to the same bucket. So here I'm oversimplifying the whole process, but in the actual LSH algorithm, we need multiple hash functions to assign the data to one hash table and many hash tables to guarantee the quality of the retrieved neighbors. Well, in the search phase, the hash functions and hash tables remain or unchanged. And when a query comes in, you will go through exactly the same process of generating hash code and find the buckets it belongs to. And this example, we can see the query belongs to the same bucket as the data 1, 3, and 4. So these are going to be the candidate neighbors of the query. Now we're ready to see how to achieve our goal of using this near neighbor search algorithm to perform the sparse matrix multiplication. Remember, like this giant matrix of our MLP layers. So what we're going to do is we're going to treat each column of this matrix as our data points we just showed. And these data points will go through the hash functions, and the resulting hash code will decide which bucket these points belongs to. And in this case, when the input comes in, you will tend to do the vector matrix multiplication. But before doing this, we're gonna hash using the same hash functions to hash this query or this input, and the hash code will decide that which neighbor is gonna retrieve, which is like tend to be 1 and 4 in this case. Then we'll simply compute its inner product with only 1 and 4. And the others will be set to 0. This way we'll get high values of the resulting vector without computing the full vector matrix multiplication. So how can we extend it to our language model inference setting? We're going to build a bunch of hash tables for the weight vectors of the neurons in each MLP layers, and also each head in the attention layer. And then here we only save the IDs of the neuron in the not the actual weights. So in this example for attention 1, we're going to compute the hash code of head 1, 2, 3, 4, and neuron 2, 4 will go to the first bucket, and 1 will go to the second, and 3 will go to the third one. Then in the query process, when our input comes in, it will go through the same set of hash functions and map this input to the corresponding hash code. In this case, we're going to map it to head 2 and 4 in the first attention layer. And we're going to compute only based on the results from the head 2 and 4. And then based on this output of the attention layer 1, we're going to treat it as the input to MLP layer 1. And in this case, we're hash it to basically neuron 1 and 5 in the MLP layer. And then we only activate it on the 1 and 5, and then compute the activation, and then so on and so forth. So basically, in summary, in this section, we can reduce the contextual sparsity prediction problem to a near neighbor search problem. And we have shown one possible algorithms called LSH to do it, to predict in advance. Next, we're going to show how we can achieve the actual speed up. So recall that our budget for this near neighbor search or any prediction is very tight. For example, like this MLP layer takes more time than the attention layer. And even for this MLP layer, it only spends 0.2 milliseconds. So that's like a very tiny budget that your overhead just cannot exceed this 0.2 millisecond. Otherwise, it's going to just slow down or increase the latency latencycy latencycy. So therefore, we really need to reduce this overhead of the near neighbor search. And at the same time, there's another problem on the implementation of sparse matrix multiplication. It's not like out of the box, it will be efficient on PyTorch, right? So basically, in summary, there are like 3 major challenges. The first one is, since this prediction is performed at each layer, so it's a very large overhead we want to reduce. The second one is the hash table of these hash functions. It's well known that those data structures are not very efficient on GPU. So if we do that on CPU, and then the speed or even the communication and also this coordination might far exceed 0.2 millisecond per layer, right? So that's very challenging. And the last one is like this sparse matrix multiplication or even vector multiplication just complicates the full implementation. And there's no out of the box ones. Okay, so what is the key insight here to achieve the actual speed up? So the key insight in one sentence summary is those embeddings are slowly changing across layers when we do the inference from, let's say, layer 1 to layer 2 to layer 3. They're not changing too much. So the plot on the left shows the median cosine similarity between the embeddings or representations at 2 consecutive layers across all layers for different OPT model size. You can see it's ranging from 125 million to 175 billion. And the trend says that the larger the model is, the slower the change is, which is intuitive. And the right plot shows that the cosine similarity stays really high, even a few layers apart. So for n equals to 1, meaning that this is consecutive layers, 2 is like 2 layers apart, and then 4 and 8. So it is still very similar. So why this happens, we're just curious. It turns out to be a byproduct of residual connection. So we plot the residual connection of this like x equals to x plus fx in the transformer blocks. They do have this residual on all the blocks, including the attention and MLP. So we plot them separately on the left and right. Left is attention, right is MLP. And the y-axis shows the norm of the original x before you add this x plus fx. Fx in attention is like the attention f, and in the MLP is like 2 linear layer with the relative. And you can see that there's a huge gap between the norm of our input to the layer and also the output from the layer. And because of this gap, which means that this x will dominate. And when x dominates, means that even you add fx in one layer, you're not going to change the direction too much. So the cosine similarity between x and x plus fx is very high. So that explains why we have this high cosine similarity of the embeddings from consecutive layers. So what can this observation enable? Well, naturally, instead of using the output from the intermediate layers to make the prediction, and we have to be like really fast, right? 0.2 milliseconds. And anything that you do a prediction is overhead. We can use the output from the previous layer, or even like 1 or 2 or 4 layers earlier. So you kind of have this like asynchronized prediction and your attention or MLP computation. So I won't go into the details here, but we can also replace the LSH or this neural network search traditional predictors with a learning-based MLP predictor, which is all matrix multiplications, so it can achieve the lower query time on 800 or GPUs. We don't need to complicate with like data structures like hash tables or graphs. And in addition to that, we also need the hardware efficient implementation. So for example, the first one is kernel fusion. So a standard implementation of the sparse matrix vector multiplication in PyTorch will separately index a subset of the matrix rows before multiplying with the input x, even if it's very structured sparse. This will incur like 3 times of the memory I/O, and we know that in the large language model inference, I/O is the bottleneck. So instead, we are going to fuse this indexing with the multiplication on the fly. We're going to load a subset of W to the memory along with the input X and perform these multiplications and then write down the results. So this fusing implementation in Triton will yield like 4x more speed up compared to the standard PyTorch implementation of separating the indexing and the sparse multiplication. And also like there's a way matrices are conventionally stored in the row major format. And this will usually allow us to load the W and if we're going to subsample the rows. However, there's special ones in this attention, for example, the output projection or MLP2. So to avoid this overhead, we're going to smartly just store those matrices in the column major format. And the last one is, if you look at the 2 red rectangles on the left, what happens to those heads if we don't compute the KV cache of a previous token and we want to generate something after that? And then it doesn't have anything to attend to, right? So the smart thing is we're exploring the fact that this latency is usually bounded by the weight loading. So as long as we don't load those QKV out projections, it's free. So we can fill in all these missing ones when that head is activated or loaded by a future token. And since the computation is free, so once I load the weights or the head, computing 1 token or 2 token or 10 token is basically the same because compute is free. Okay, so we're excited about the last section of Deja Vu, which is evaluation. So let's look at the first one, which is evaluating mostly on the accuracy or performance part on the language modeling task and also like downstream task. So this 3 plots shows the accuracy trends for Deja Vu OVT 175. It's like the largest OVT model. The first plot is language model, and then the second one is like the 0-shot performance. And the x-axis is like the sparsity percentage. The higher, the faster, but also tend to sacrifice the accuracy, right? But we can see a trend on where it cut off appears. And the last one is like the 5-shot. It's like there's 7 tasks. So the takeaway is saying that it occurs no accuracy drop until 75% of contextual sparsity. So a small note here that because MLP and attention have different number of parameters or different kind of latency breakdowns, usually MLP is 2x than the attention. So this 75 is after balance, all of them is like end to end. Therefore, we usually observe a sparser MLP, but comparatively denser attention when we calculate this contextual sparsity. Okay, the next evaluation is our speed. So we just look at the accuracy and the speed, and it follows where the breakdown is on the attention and MLP for a total of like 75%. And compared to, again, faster transformer in C++ and Hugging Face is 1.8 to 2.5 times faster, and widely, and also like 4.8 to 6.8 times faster than the Hugging Face. And this result holds across different sequence lengths or prompt lengths. A small note here that we usually get like lower speed up with like longer sequence. The reason is when your sequence length starts to dominate, there's a significant amount of time that is wasted on the inefficient implementation of attention, and plus like the KV cache loading. So what I say about like this 2-to-1 latency breakdown of MLP and attention only holds when your sequence length is pretty small. So, okay. So the next evaluation is what would happen if we combine the sparsity with the quantization. We see a line of work on that, right? So it seems like the combination will always achieve better accuracy than either like Deja vu or like sparsity alone or quantization alone, which is kind of interesting because before doing this ablation study, I thought since quantization introduced some errors and sparsity also introduced some errors, they should compound. But surprisingly, they're also compensating each other. So, which is great news, at least empirically, but we don't have a very good understanding why. And we also evaluate on the variable batch size. So although our best case, or what we call it 2.5 times speed up over the state of art, is on batch size 1, because you can observe that this low latency setting means that you're gonna have fewer inputs, and our contextual sparsity is actually very sensitive to how many inputs you get. So the more inputs you get, you tend to activate more neurons or more heads. And at the end of the day, if it's too much, you have like zero savings, right? But surprisingly, we still get reasonable speed up, even up to like batch size 32. With like batch size 32 and sequence lengths like 1 to 2,000, we're almost out of memory for 880 gig. So this is like very reasonable performance if we're not aiming for the high throughput setting. So, and the bottom table just show you that why we still have a lot of saving in like 32 batch size. So theoretically, if the contextual sparsity is kind of like uniform, so one input will have like, let's say like 2%, and the 32 will have like, 5%, and the 32 will exploding the 100%, right? But it's not actually true in our setting. Here's an example of that sparsity on layer 40 MLP. So which means like we have some heavy hitters on the contextual sparsity of input tokens, so that even 32 is not scaling linearly with the density. All right. So the next evaluation is on different model families. For example, Bloom, which use Galu instead of ReLU. We can see that compared to the OPD family, which is ReLU, which is strictly 0, right, after the activation. The speed up is like lower, only up to like 1.6x. I think it's like because of this Galu and ReLU difference. And I believe it's the last evaluation is on the our sparse implementation, MLP implementation. It's just like evaluation on how well we scale. So the plot on the left shows the scaling of the sparse implementation, sparse attention implementation, and the right is the sparse MLP implementation. So it is up to like 5 times faster than PyTorch, the naive PyTorch, and can still remain faster than dense matrix multiplication for density up to 80%. All right, I think that's the end of the evaluation. And here's several future work or near future work. So in the work of Deja Vu, show an implementation on A100, which is the best or arguably the best that H100 is coming hardware. But we can obviously view this Deja Vu as a framework, an algorithm, and can be extended to a more low-cost GPU or even CPU to enable more like general accessibility of large language models. You will actually have benefits if we implement these algorithms on commodity hardware, because remember, like we spend a lot of effort and time and all this like understanding and tricks just to get this 0.2 milliseconds optimized. And in the commodity ones, there's like the headroom is larger, and maybe the algorithms that we can use can be like other near neighbor search algorithms, right? And the second one is like we kind of made an observation on this nonlinear increase of the density when we increase the batch size. So there's a chance of even for aiming for high throughput setting, we can maybe batch similar inputs and still get efficiency out of the contextual sparsity. And the last one is like, yeah, there are a lot of other problems, like, for example, long context length, KV cache problems, and many more waiting for us to solve. I think this is the end of the talk. Thank you so much to join me today, and I hope you enjoy it. Happy to take any questions.
Thank you, Beidi. Very, very interesting talk. Questions from our audience? You can unmute yourself if you want to have some questions.
Hello, Dr. Chen.
Hi.
Yeah, thank you for your excellent talk. Yeah, I'm a student advised by Dr. Yuan. Yeah. So I was curious about the contextual sparsity. Is it to use some simple technique like LSH to reduce the complexity of computation of tension? Does my understand? I mean, is my understanding correct for?
Yeah, so in general, I think that's the main idea. However, there's a problem with like just using LSH on MLP or attention, because the setting that we choose is the high performance and low latency setting. So we have to replace this LSH algorithm with other gem-based method, like a trainable MLP, which we can just deploy it on A100 without communicating with like CPU and complicates the implementation. But the general idea is very similar.
Okay, so basically, in the original attention computation, so we have to compute all the like the connection between one token to all others, right? So you use this sparsity, like the sparsity to reduce the complexity. So my second question is, what is the motivation for for LSH instead of other like simple, like simple computation alternative to compute the sparse attention? Yeah, so I'll answer your questions in twofold. First, so there's a very easy to misunderstand part on what are we optimizing on the attention. So we're not optimizing the number of attention computations in the inference, because for one token generation is only 1 by s computation as the sequence length. So it's nothing compared to, for example, weight loading, like those QKVO projection loading, or those weights
from the linear layers from the attention, they're actually the bottleneck in the inference. So that's what we're optimizing for. And the LSH or near neighbor search algorithm is to find the attention head that you don't need to load from your GPU memory to tensor core. So that's to answer your first question. The second one is, even under this setting, yes, your second question still exists, right? Like why LSH, why not other ones? Like what I said, we also try like HNSW and also like all the other near neighbor search algorithms, but none of them can get us the extreme efficiency. And to be very clear, we didn't use LSH because LSH introduced this hash table lookup, which is not efficient on GPU. So we only use a MLP, small MLP layer to predict, but the functionality is the same as LSH or the other examples that I gave.
Okay, thank you. Thank you for answering. Thank you.
Yeah, thanks.
And thank you again for an excellent talk.
Glad you enjoy it.
Yeah.
Other questions? Other questions from the audience?
Hi there. This is Zhang Wei from IBM Research. A very impressive talk. Thank you very much. I just have a question. I'm wondering if you happen to have this trade-off with latency or your final model performance. Would it be reasonable to compare, say, if I have a teacher-student model to do some distillation, so that you shrink your 175 billion parameter to a reasonable size and also achieve the same kind of latency bound, and what would that be a trade-off compared to your approach?
Yeah, so the largest problem these days of a large language model era, because distillation, same as quantization, quantization, pruning, distillation, right? Like three major methods of approximation or relaxed algorithms. So I haven't seen, or maybe I missed something, that even the sparsity is very minimum. Majority of the algorithm relaxation on quantization, I would guess is like it can get efficiency and it's easier to pre-process. But for the distillation and pruning, it's probably taking some like retraining or touching the model. No one wants to retrain like 175 billion, even like 60 billion like llama model. No one wants to like retrain it, right? So that's what I guess would be the reason that there haven't been work or not as far as I know that work on this. But I much believe so. I think we can distill the large models, but we just need a more efficient algorithms to distill it. And not sure if OpenAI has already done it. But I think that's if it exists, so we definitely should compare to that. And maybe there's I don't know, maybe it's also orthogonal. Maybe we can distill it, but not to the level like 100 million, right? You still can have like maybe 6 billion or like 10 billion is kind of reasonable size. Then I have been showing this experiments, but we can still get reasonable speed up. It's just not as impressive as the 175 billion in a smaller scale. Yeah, hope that answers your question.
Oh yeah, certainly. Thank you very much.
Other questions? So Beidi, I have some questions. Yeah.
Yeah,
so
sure.
I remember there's one slide you mentioned that for some kind of the system level optimizations to make it become more hardware friendly, and you need to do some kind of kernel fusion and so on. So I was wondering, so how about this kind of the effort at which type level of the code it is doing on some? You need to rewrite some like the CUDA code for that, or?
Oh, we just use Triton, which is a little bit higher level than CUDA. But the lower level you get, the more speed up you get. So we're pretty happy with like 2 point something X. So we stop there. But it's not optimal. I know it's not optimal.
Okay. And also, so I know that actually you and your group actually works on several different type of optimization techniques, like for example, your scatterbrain and those work. So I was wondering whether this, like the work you present today, can be further combined with some prior works together to achieve kind of better performance.
Exactly. So there's one functionality which says that in scatterbrain, which says that it's a drop-in replacement of current attention, right? So they are attention, for example, like linear attention, etc. They require to modify in the attention layer, and they're not like dropping. But scatterbrain is kind of like a drop-in replacement. So I think this can be directly used in the inference, and especially in the high throughput setting that we didn't touch today. Because in the high throughput setting, if your sequence length is long and your batch size is large, then KV cache will dominate compared to the weight. So in today's like latency-based setting, is basically like weights loading IO dominates. So optimizing attention or not does not matter that much. However, in the high throughput and long sequence length or long context length setting, you will play a major role there, and you can definitely complement what we present today. Yes.
And another question is that so today at the beginning of the talk you mentioned about like the motivation is because of it's different from the like vision transformer and so on. I was still curious about whether we can like apply this approach to the vision.
I think there's no problem of applying to any of the setting, but the problem is mainly on the sequence length side. For like VIT, for example, classification, all this like sequence length can be paralleled. And then in our case, it's similar to like high throughput setting. Once this can be parallel, first is problem may shift from memory or like IO to compute. And second is like sparsity there might be unstructured if we just use it out of the box. So it needs more work if it's applying to the standard setting. So yeah, you will face the same problem when I was training like slide or some previous work. And that was the reason why I chose CPU to do that. It's like those sparsity or algorithms just not very efficient. So this is one of the important setting and kind of the paradigm for this kind of sparsity. So I was pretty happy.
And also, so here, so your major scenario is about the inference, right? And
Right.
you mentioned because for the training, so actually we can have, so there's no kind of the dependency within the sequence, input sequence, right? But I was still wondering that, so since you can reduce the kind of the complexity in the forward pass, whether it's can still kind of bring some benefits for the training. Have you ever conduct some kind of the study for that?
Yeah, we're actually looking at it right now. So the problem for the training is you can view this as a more fine-grained mixture of vector model. It's just like each neuron or each head is an expert. So in the memory bottleneck setting, it makes sense because it's just bottleneck by how much you load, then you save how much. And then usually one neuron is at least 128 consecutive floating points, right? So you always have speed up. However, in the training, the major bottleneck is how do we revert this kind of sparsity into a more structured, for example, kind of a MOE-like sparsity. Then in that way, we're gonna have like speed up in the training. And in the training, it's mainly compute bound, right? So it's like SDD multiplication, like sparse dense dense, and then you want the sparsity to be structured. So once you have MOE, as long as it's like above 128, we can also get the like this kind of efficiency. But the challenge is how do you organize those fine-grained neurons into a coarse expert? Maybe we can. That's what we're investing right now. Yeah, it's like a reverse problem.
Thank you. Thank you very much. And any questions from our audience? Okay, so if no more questions, so let's thank our today's speaker again. So maybe I enjoy your talk very much. So it's very, very inspiring. Yeah.
Thank you.
Okay.
Hope everyone likes it. Thank you.
Yeah, I believe so. Yeah. So also thank everyone to attend our today's seminar talk. Okay. Thank you, Beidi.
Yeah.
Have a wonderful day. Bye.
You too. Bye.
Bye.